So here we're just going to recap an introduction to the normal distribution. So there are some features of the normal distribution that we must be aware of. The normal distribution is probably one of the most popular distributions within statistics, within mathematics, and that is because it is a naturally occurring distribution which we get in nature, which we get in the population of people. It just occurs on a regular basis. If we were to measure the heights of 14-year-olds, they would adopt a normal distribution, with the majority of those 14-year-olds having a height close to the mean, with very few of those 14-year-olds being extremely tall, and with very few of those 14-year-olds being extremely short. And this is just true for lots of different things. If we were to measure the lengths of leaves, if we were to measure the amount of rabbits, or if we were to measure people's estimates, if we were to measure so many different things, they tend to follow a normal distribution where the majority is located close to the mean, and there are two similar tails, which leads to symmetry. Okay, so the features that we want to discuss are the bell curve, so two tails and a peak in the middle. This leads to the next point, which is symmetry. So the normal distribution is symmetrical. This is going to be a very powerful feature as we continue with our work on the normal distribution. Being symmetrical means there is no skew. And if you remember previously, we could determine skew by the location of the mean, the mode, and the median. So interestingly, the mean, the mode, and the median of the normal distribution are all located in the same place. So this blue dashed line should represent the mean, the average value, the mode, the most popular value, and the median, the middle value. All right, so this is a condition, or this is a property of the normal distribution. And next, the fact that the area under the curve represents a probability of 1. We're going to use our normal distribution for problem solving based around probability. And a key fundamental point is that the area underneath this curve, which we could have found through integrating, is going to total to 1. So the area below the mean is 0.5, and the area above the mean is also 0.5. So that's a starting point, but we're going to look at lots of other ways that we can split up this normal distribution graph and find other differing probabilities. Okay, so 3 aspects, 3 properties, 3 characteristics of the normal distribution. It has a bell curve, it's symmetrical, and the area under the curve represents the probability of 1. Another underpinning characteristic of the normal distribution is that actually the normal distribution is a continuous distribution. I'll draw some more emphasis onto that in a little while. Okay, so we already saw that below the mean there is going to be 50% of our data, and above is going to be 50% of the data. And that makes sense because that point is both the mean and it's the median. So we should be happy that the median splits our whole distribution into half, or into halves, with 50% being above that value and 50% being below. There are some other values that we do need to be confidently aware of, and they are as stated. So we can identify where the mean is. Up to now, we've been using X bar because that is the sample mean, but we are more going to use mu, which is the population mean. All right, so mu just indicates where the mean is, and we're familiar with the standard deviation. I'm going to say that this point is mu plus 1 standard deviation, and this point is mu minus 1 standard deviation. So in this range here, there's a specific amount of data, and that is 68%. 68% of the data for any normal distribution exists within 1 standard deviation of the mean. Okay, so this is 68% of the data. We can carry on from that and actually say, what about within 2 standard deviations? Well, within 2 standard deviations, so this whole area here, we're going to have 95%. Okay, and within 3 standard deviations, we'll have 99.7% of the data. Almost all of the data is going to exist within 3 standard deviations. We're going to get 99.7% of the data existing between there. It is almost all of it. I only have 0.3% left beyond the 3 standard deviations. But just be careful that the normal distribution, actually being continuous, goes on to infinity, positive infinity and negative infinity. So technically there is still area that exists to the left and to the right. A very small and negligible amount of area, a very small and negligible probability, but it does exist, and it's important that you understand it's actually there. All right, so these values, 68%, 95%, and 99.7%, these are values that you need to be extremely confident with and to know that they exist within a particular amount of standard deviations. Okay, and those can be seen a little bit nicer on this diagram, where each of the segments are split up into 34% and 34% above and below the mean, and then these 14% in between the two standard deviation and the one standard deviation markers. How we're going to start to find probabilities for different probability statements. All right, firstly, let's get into some notation. Whenever we do set up a normal distribution, we say that X follows a normal distribution for a specific value of mu and a specific standard deviation. We always write the standard deviation squared, which is actually the variance. This is just a convention. You need to get used to it. Always write that as the standard deviation squared. Be on the lookout for questions where they've given you a value of the variance. You would still need to write that in the form of the standard deviation squared. Okay, so this is the general form of the normal distribution. Let's see if we can start to answer some specific questions. So, if X followed a normal distribution of 10 with a standard deviation of 2, a few questions we should be able to respond to. What is the probability that X is less than or equal to 10? Okay, well 10 is the mean, so the probability is less than or equal to the mean, 0.5. Okay, what is the probability that X is less than or equal to 12? All right, so being really careful here, 12 is the mean plus one standard deviation. Mean plus one standard deviation is all the area contained under here. I already knew that everything on this left-hand side was 50%. Now I just need to add on this extra 34%. So the probability that it's less than or equal to 12 for this particular normal distribution, 0.84. By recognizing how many standard deviations we're working with, we can use some of these standard probabilities to go ahead and work out our answers. What about the probability that X is greater than or equal to 12? Once again, 12 is one standard deviation above the mean. So this is the important value. And I'm looking for everything above here. It would also be smart to recognize that it was everything that I didn't include in my previous answer. So 0.16. Okay, let's see if we can ask some slightly different questions. What if I wanted to know the probability that X was in between 8 and 12? Well, 8 is one standard deviation smaller than my mean. If you like, I can write it out like this. And once again, we should recognize that since this is the mean plus and minus one standard deviation, I'm looking at this area here, this region, which is the 68%. Okay, so by making use of the 68, 95, 99.7 rule, we should be able to answer quite a few questions. So on this one, it's two standard deviations below and one standard deviation above. So this is the region I'm now looking for, and it's 0.82. Okay. Okay, so let's try one that's a little bit more problem solving. Here we're told that the masses of chickens, m kilograms, on a farm are modelled as m follows a normal distribution, mu sigma squared. If 99.85% of the chickens weigh more than 1.3 kilograms and 97.5% of the chickens weigh less than 2.8 kilograms, we're asked to find mu and sigma. I'm going to start by trying to place some of these on the diagram. 99.85 weigh more than 1.3 kilograms. Where on the diagram is a point that is exceeded by 99.85%. Well, that's going to be right here. Mu minus 3 standard deviations. There is 99.85% above this particular point. So that's where the 1.3 kilograms is going to go. 97.5%. Where on the diagram can I mark to show that 97.5% of chickens weigh less than this value? Well, that's going to be here. This is going to be 2.8 kilograms. Now that we have those set up, I can actually set up an equation to link the mu and sigma expression with the weight. So mu minus 3 sigma equals 1.3 and mu plus 2 sigma equals 2.8. And I'm sure you can see it. Here we have simultaneous equations. So let's go ahead and eliminate mu. I can do that if I take equation 2 and subtract equation 1. That gives me 5 sigma equals 1.5, which means sigma equals 0.3. The standard deviation for the masses of these chickens is 0.3. And I can substitute this right back in again to find mu. So substituting into equation 2, mu equals 2 plus 0.3, which gets us 2.8. The mean is 2.8 minus 0.6, 2.2. So the mean weight of the chickens is 2.2 and the standard deviation 0.3. Be fully aware of this rule and how it can be useful in finding out probabilities, as long as we think about these values in terms of the number of standard deviations they are away from the mean. Okay, and we're just about finished, but before you move on to some practice questions, let's take a quick look at the specification and exactly what it is that students are expected to be able to show, exactly what the examiners are anticipating you will be confident on. While you read through that, I want to quickly remind you that it will be sensible for you to come back and watch this video at a later date, maybe come back in 2 or 3 weeks or before an assessment. And as you watch through the second time round, because you've done your practice, a lot of what you go through here should resonate with you much more. And you have a chance to really embed your understanding of the difficult concepts, the ones that have been flagged up as A star.